I've been waiting for this day for the past 3 months, and I've spent almost a full year learning about how this device exactly works on this YouTube channel. Really, the birthday of this YouTube channel was last July, and we only talked about computer architecture for nearly a year, and it all led up to this point right here. Because now we're done with the simulation, and we're going into real life electronics. How do computers work with electricity? Not just how can we do binary math, how can we manipulate bits to make a simulating computer? How can we actually control electricity and to get a fully working computer? And we're gonna learn about that today, officially. I spent literally the past 3 months talking with sponsors. This video is sponsored by Next PCB. We're gonna talk more about them later. So I talked with sponsors. I designed the circuit. I started the circuit. I had to come up with the code and etc. And it wasn't perfect. I had so many flaws within making this computer and the process, and I'm going to show them all right now so you can learn from my mistakes in case you want to build your own, and so you can learn how a computer works instead of just hearing the basic stuff everybody says online, which is your computer has 4 cores, your computer sends data to the RAM goes to the GPU. I want to know exactly how the CPU sends data to the RAM. What does it do? What does it turn on and off? How does it control the electricity? And that's what we're going to learn right here. So a little background too. We already explored physical computers with the one actually right here. And that was a transistor computer using bipolar junction transistors. It sucks though. I'm going to be completely honest. It is pretty trash. It can only add numbers, but that's still pretty cool actually. We can add and save numbers with transistors. But I want to do a little bit more than that. So we can program some useful stuff, and we can program some cool stuff too. You can see our computer actually run and work in real time. And so I could do that with transistors, but that's going to take like 2,000 transistors. And guess what? I already made the circuits coming in, so that is happening. But I want to make something that doesn't take 2,000 transistors. It's a fully functioning 8-bit CPU, so we can do 8-bit math. And I want it to be pretty versatile. I want it to be a fully programmable, turning complete computer. And I did that. And this is the final product. This is my 8-bit computer running the Fibonacci sequence. And so you can see it working in all its glory. And we're going to go over this code in the middle of this video. But this is a little edit of it actually working. So how does this computer work? And I mean like, how does it work in like full-fledged detail? So let's go through it step by step, how it works. We're going to start all the way at the left side. We have the HC4060. This is our clock. This is the heartbeat of our CPU. So we have a 32.768 kilohertz crystal. I don't remember the exact number of what it is, but it's around there. I know that for a fact. We have that crystal, so we get a perfect 8 hertz signal, 4 hertz signal, or 2 hertz signal, depending on how we control these LEDs right here. So these LEDs allow us to put different clock signals to our CPU. And we have this LED right here that will show us our clock signal of the CPU. And so the clock signal is going to get fed to this HC161, kind of way over here. And an HC161 is a binary 4-bit counter. And so we can count from numbers between 0 to 16, or 0 to 15, it's binary, 4 bits. And so on every 0 and 2 bit, we're going to increase our program counter by 1. And so you can see this happens 8 times, this happens twice every 8 clock ticks. And so we don't need all 16 bits on this 161 to make the computer fully working. We only need 8 bits. So every 8 bits, our program counter is going to increase by 2, essentially. And this program counter right here controls our most basic function of the CPU, which is fetch, decode, execute. This all happens within 8 clock pulses. We fetch, decode, and execute. Okay, and so now let's go back to these other counter chips. The same chip, so the HC161, but this is our program counter. We have two of these because we have an 8-bit program counter, so we can store programs between 0 and bit 255, essentially. So our program counter then gets fed into our ROM chip. This ROM chip contains our code that runs the computer. This is the code that's going to be like add to, save to accumulator, display data, essentially. And this code is then going to get fed into this code is going to get fed into these two HC273 chips. So what are these chips? This is pretty much just an 8-bit register. And so this is going to allow us to save our code for decoding. And so we're going to save it to the opcode register, and then we're going to save our operand to the operand register. And then the opcode register is going to get fed into another ROM chip, and the operand register is going to get fed into a tri-state buffer. So let's go with the opcode first. It gets fed into this ROM chip. This ROM chip contains our microcode. So whenever I say add to, how does our computer know what to do next? And that's with the ROM chip. The ROM chip contains all of the data that the computer needs. So when it sees, hey, opcode 1 has been called, it can associate opcode 1 with actually executing add to, essentially. And so it contains all of our microcodes, essentially. And so this ROM chip, its output gets fed into these HC138 chips, which are 3 to 8 decoders. So 3 pins on the ROM chip control 8 outputs. And this allows us to control all the different modules of the computer. We can control the save pins on our accumulator and our other registers. We can control the clear pins, the output pins, the add pins, etc. And we have 3 of these, so we can control multiple, objects at one time, or one clock pulse in the CPU. And you'll see this in a second. So let's go back to our operand register. That gets fed into this tri-state buffer, which then gets fed into the bus. So if we have a code that says load immediately into accumulator, essentially what's going to happen is our ROM chip, our microcode ROM chip, is going to activate this tri-state buffer in order to allow it to output data onto the data bus, which will be 2. And then our microcode ROM chip is going to keep it activated and then press the save button on our accumulator register so we can save 2. And so you can see how this works because the tri-state buffer and the save to accumulator are in 2 different HC138 decoder chips. So we can activate them both at the same time. And so if we keep moving forward, we see our 2 registers, our accumulator and our register B. The accumulator is connected to our ALU on the A inputs, and register B is connected to the ALU on our B inputs. But that does bring me into a little situation. Our B register actually goes through a set of XOR gates first before it goes into the the ALU, so we can have a subtract feature. And then our ALU inputs and our register B inputs are all connected together, which is connected to the output of ALU. So we have this data bus right here, which is also connected to the tri-state buffer, which is the HC245. And then our registers, our accumulator and our register B, we said it's connected to HC86, which is XOR chips, and that's connected to an HC283 chip, which is essentially just a 4-bit adder, a 4-bit full adder with a carry in and carry out input. We have 2 of these to make an 8-bit adder. And then we have these 2 chips on the sides right here. This is our comparator chips. So they pretty much say, are the 2 numbers that are going into ALU, are they equal to each other? Is one greater than, or is one less than each other? Which those outputs allow us to biconditionally branch our computer when we want to jump. So let's say we had these 2 numbers and we're saying if 7 equals 7, we want to jump to program 100, for instance. That's what those comparator chips allow us to do. They allow us to make the equal pin high if the 2 inputs are equal. And then we have this HC74 chip, which is just a is just a data flip-flop with a set and reset pin, and this gets fed into our carry input. And so we can essentially set the carry input as high if we want to add numbers that are larger than 8 bits together. And the carry output is fed into the input of this data flip-flop, and the carry output is also fed into another circuit so we can jump if the carry is high, essentially. And so the output of our HC283 chips goes into this HC373 chip, which is a data latch and a tri-state buffer combined. So it's a data latch, not a data flip-flop. So that means if the save signal is high, the data will pass right through it. So it doesn't save on a rising edge, it just saves if the data is high. And then we have this tri-state output too, so we can make the output of the data latch high impedance or whatever is saved in the data latch. And this is connected to our data bus. So we have two tri-state buffers, outputs connected to our data bus. So we can control which one is on and which one is actually sending data to the data bus. Naturally, the 373 is on unless we tell it to turn off. And this allows us to not have the data bus at high impedance ever because the HC chips hate high impedance. If there's a pin on the HC chip that is not connected to anything, it's going to start drawing in a lot of current. And so we have to make sure all of the inputs on our HC chips are not floating. They're connected to ground or power. And that brings me to my next point of why did I choose the HC chips if they're so hard to work with, because we have to make sure everything's grounded. Because the 7.4 LS chips don't have this issue. But the 7.4 LS chips are BJT, they're bipolar junction transistors, which means they draw a constant current even if they're idle. So that's not really ideal because I don't want to really spike my electricity bill up and draw a lot of current. So we went with the HC chips, so we draw minimal current because they only draw current when we're either A, outputting to an LED, or B, switching states. And so this computer at 6 volts draws about 100 milliamps of amperage at most, at absolute most. And so it's pretty efficient, I would say, in that aspect with about 0.5 to 0.6 watts of power consumption. And so that is pretty much everything you need to know about the computer. We can talk about the LEDs real quick. The green LEDs are this program, so it tells us what program number we're on. The white LEDs are operand. The yellow LEDs is our opcode. The red LEDs are ALU output. The blue LEDs is the bus output. And so we can essentially read everything we need to read with this computer. So one little quirk about this computer is that on our 8-bit instruction cycle, bit 0 and bit 2 is our save inputs into our opcode register and operand register. So let's say we have the command save accumulator, but it's not save a certain number. We're still going to have an opcode space because every instruction takes 2 spots up on a ROM chip. So instruction 1 will take spot 1 up and 2 up. The opcode will take spot 1 and the operand will take spot 2, essentially. And so then we go into our other instruction, I guess, bits, you could say. The first 4 bits are for fetching data, and then the last 4 bits are for executing data, essentially. And we decode the data automatically, you could say. So we don't need an actual physical CPU push to decode the data successfully. But that is it for how this computer works. I made this computer in 2 simulators. So we're going to go into the simulation and we're going to see with a different kind of perspective how this computer works, so you know exactly how to make a CPU from scratch, and there's nothing hidden about this at all. So we are back in our digital logic simulator created by Sebastian Legue. It's free, so if you want to download this and fool around with it, you can. But this is where I make most of my simulated computers in, and this one is no different. This one's the IC chip computer because we're using integrated circuit chips. And so you can see I have all of the names down here of each of these different chips, all of the ones that I've essentially talked about. So if we go into our computer, I have a lot of different stuff I'm trying to fool with right now, but let's just go into our actual computer called computer. And this is just what I labeled the CPU as, these just bits. The F stands for full XOR, 8-bit computer. It's the 0th generation, the first generation, essentially. And this is our Fibonacci sequence right here. This is the program to run the Fibonacci sequence, essentially. But as you can see, it's not in here right now. We only have 2 numbers. I did make it successfully in the simulation, in which I guess I could play a little preview of it after, even though it really doesn't matter. Yeah, sure. I'm just going to play this a video of the simulator doing the Fibonacci sequence, so you know that this does work most of the time. But sometimes the simulator does glitch out a little bit and it doesn't really work. But it's still a really easy way to see if your circuits behave properly. So that was a little bit of the Fibonacci sequence that we had right there. Not really the whole thing because it will take a while, but let's go into our actual computer, our actual CPU of everything. And this is it right here. So I'm going to press tab and we're going to see the whole computer right here. And this is everything I talked about in my little talking head segment from earlier. This one is labeled wrong. This should be a 373, I'm pretty sure. Let me look at my physical thing real quick. It should be, yes, a 373, not a 574. But everything else is correct. So this is our tri-state buffer we were talking about, our 2 registers, our ALU, our program counter, and our control unit. And you can see how the output of our ALU is fed into this register, this little buffer register first, which is then sent to our data bus right here. And so let's look at our control unit first. So our control unit has these HC138 chips I talked about earlier. It also has this 161 that controls our 8-bit instruction cycle. I did forget about this decoder right here, which just decodes our instruction cycle. So we know what to do every 8 bits, essentially. You can see that on the 0th bit, we save the opcode, and on bit 2, we save our operand, just like this. So, and we do that every 8 cycles. So I'll kind of, oh, we're in the control, yeah, I can't play it, or simulator right now, but just trust me on it. And so this is our opcode register, and this is our operand register in the simulator. It's fed into our microcode right here. This is our ROM microcode chip, which is then fed into these decoders so we can control different units at one time, as you can see with this right here. And then this right here is our little logic that's on our physical CPU 2, so we can successfully jump depending on certain ALU outputs. These are our ALU flags, you can say. These are the flags, and which allow us to jump to certain things. But that is essentially how the program control unit works, excuse me. The program counter is just 2 161 chips, essentially. And if you want to, you can see how the 161 chips work. This is the exact schematic that you'll find online about how they work. I just made it with logic chips in the simulator. And so that's pretty cool. And then we have our ALU, which is just our 283s, because these are adders, essentially. And then we have our XOR gates, which is the HC86 chips. And then we have this is our data flip-flop, essentially right here. I just made it with actual individual chips instead of a real data flip-flop chip. But it behaves the exact same as the HC74 chip we have. The only thing different is my first design was this HC688 chip, which is essentially just one big like 0 kind of pin. So it takes in 2 8 inputs and outputs a high number if they're different and a low number if they're the same, essentially. Or yeah, essentially. And so that was my original plan, but then I scrapped that and I went for the HC85 chips. And so those are the comparator chips I was talking about earlier. And so that is essentially how this whole computer works as of right now. And so let's go into our control unit and we're going to kind of see how this works in real time. So when we clock it, you can see that the save goes high to this opcode register. We clock it again, and then we clock it again. Excuse me. Actually, we weren't on 0 to begin with, so that's my bad. So now we're on 0. We clock it one more time to start it. So this pin went low, so we're going to save our opcode to this thing right here. And all the outputs on these chips are all naturally high, and they're low only when they're called, which is kind of weird. We haven't really done anything like that, but it's kind of an inverse chip. And so when we clock it again, we clock the program counter right here. That's what this output is. So we increment the program counter, and then we save our operand, and then we increment the program counter again. And then we go into our execute code, which is essentially whatever the microcode has, we're going to execute it. So let me see if we have an instruction for me to demonstrate. So we do. So I'm going to press 16, right? That's 16 2. So it's going to be 2. So opcode 2, when we reset the system, you'll see we saved the opcode. Now I'm going to turn it off. That was kind of weird. That kind of just glitched out. I'm just going to keep it on for the sake of this part of the video. So we're going to save 2, and we're going to save 2 to our operand, even though it doesn't matter for this. And now we're going to go into the execute part of it, and you can see the save A turned off because we're going to save the accumulator. And then when we clock it again, it turns back on, and then we save data to the accumulator. And that's because this 161 chip is also connected to our ROM. And so when we call 2 is starts at bit 16, and it does 16, 17, 18, 19, 20, and 20 is 8, and 8 corresponds with the save address to our accumulator. And then we have 21, 22, 23, and 24 is our last code, and then we restart the cycle. So hopefully that made sense. You can see how it's connected to our ROM chip like this, essentially. And again, like I said, it controls the whatever we want in our CPU to be controlled. So that's how our control unit works, which is by far the most complicated part of this thing. And so that's pretty much it for the simulator that I can think of. Yeah, so that's pretty much it for the simulator. Now we're going to go into another simulation that I made, which is Logicism. And it actually has a fully working code on it, and we can see it executed on there. But it's just a different simulator because this simulator is sometimes not reliable with actually simulating the computer accurately. But Logicism is a little bit more accurate, and it's, instead of it being based off of chips that you make, it's based off of real physical chips. So it's a lot better to simulate a physical computer on Logicism than it is on Sebastian Legu's DSL. Okay, so we are on Logicism now. You can see it's a completely different look about how the computer works, but we use the physical chips instead of created chips that we would have to design like in Sebastian Legu's DSL. So this is a lot better simulating a real life circuit. You can notice all the chips are the same. I didn't add every single chip into this simulator yet. Like, I don't have my 2 comparator chips, and I don't have my carry input data flip-flop saver yet, because we don't need them for the Fibonacci sequence. So I just didn't add it in because I was just kind of concerned with making the Fibonacci sequence work. So if we go over here too, I want you to notice something else, and that is we don't have a register. Where's our register right here? Where's our 373? And that's because Logicism doesn't have a 373 register or register tri-state buffer kind of combination. And so we don't actually have it in the simulator. So the next best thing we can do is just add a tri-state buffer, which is what I did. So this HC245 is going to act as our 373. And then we have the original 245 right here in the bottom for our operand. And so that's enough. We're going to actually run our simulator. So this is our program. This is our microcode. And we're going to see the Fibonacci sequence start. So we're going to press Control K. the clock signal is going to go high. And then if we go all the way over here, we can hopefully see our data bus output, and then we can hopefully see our ALU output. Excuse me, I could not think of that. But first we need, let's see if this works. First we need some data on here. So we just cleared all the registers. This is moving a little slow, so I'm gonna increase the frequency to 16. And so you can see we're doing the Fibonacci sequence right now. So 3, 5, then we have 8, 13, and so on. So it works well in the simulator, and it also works well in real life, which we're going to look at next. But this is it in the simulator, and the real life one uses a very similar code to the one within the simulation. But this is pretty much all I have to say about Logicism. We're going to use this one a little bit more probably in the future, just because it's a little bit more reliable than the Sebastian Legu DSL. The only bad thing about this one is it's really hard to zoom, and I really haven't like kind of maxed it or figured it out yet, because you don't use the control wheel to zoom. You have to use this little slider right here. So that kind of sucks. But that's my only complaint about this. Otherwise, it's a phenomenal app. It's free if you want to download it, and you can mess around with your own circuits within this app. And it's a little bit more accurate too, because you have to ground certain pins in order to make this thing fully working. But that is it for this. So before I start with the physical CPU, let's talk about our sponsor first. And so we're going to roll into our sponsor. So this is our sponsor for this video. This is Next PCB. And like I said, they're the ones who helped me make my 8-bit CPU a reality, and I'm so grateful for them. So this is our website right here. You can easily get a PCB quote. You can do standard PCBs, advanced PCBs, PCB assemblies, so they can put all the components on there for you, which are their two main services. Like I said, they have other types of PCBs, flexible, rigid, aluminum, kind of whatever you want. It's standard. All you got to do is put in your Gerber file for the PCB into their website, and they're going to give you a direct quote, and they can also ship to most places in the world. So I live in the US, and they easily were able to ship it within the US. No questions asked. Their customer service is also pretty good. They kept in contact with me throughout the creation of this video, and were patient with me enough while I was making this video, because I did take a long time. This took about 3 months, I would say, of making in the background, along with doing other schoolwork and making other videos. And so I appreciate their patience with that too. But now my project is pretty much fully complete, and the video is happening right now. That's pretty much all I have to say about Next PCB. Thank you so much for sponsoring this video, and link in the description if you want to check out their website. They also have a promo code for $200 off. Yeah, but oh well, they also have their promo code coming, and if you're a new customer, it looks like you get $20 off for new customers. So please visit my friends at Next PCB for all your PCB needs. I'm going to show a little quick quality check of the PCB. It's very high quality. I had no problems with it. It's exactly what I designed, which is a problem because I designed some things wrong, but they didn't mess up a single bit. They put immense detail into the PCB. But like I said, thank you so much for sponsoring. And now let's get back to looking at this beautiful 8-bit computer circuit. So this is going to be a little demonstration about how this computer works right here. And I'm going to start it purely from like start, with literally no electricity going through it. And I'm going to show y'all how it's going to start and how it's going to run. So the program we have in it is the Fibonacci sequence, of course. And the way it's going to work is it's going to clear both the registers, our accumulator and our register B. And then we're going to load 1 into the accumulator. We're going to load 2 into register B. And then we're going to add and flip-flop between the two registers that we save in. And we're going to look more in depth into this code after this, but I do want to give the demonstration behind how it runs in this full thing. And once the carry unit, or once the numbers get too high for us to output on our 8-bit output side, we're going to reset the program and just start all over again. And that's pretty much how it's going to work. So this does use a biconditional branch. We're going to jump if the carry is high. And so we're going to see this in action and show that this is a turning complete computer thanks to our little biconditional jumping mechanism. But let's just get the program started right now. That's a good little intro. So let's see, let me get this in frame. We got to reset it so it resets. Okay, so we reset effectively. So this is our program right here. It's going to tell us what program we're on. So right now we're on 2 and so on. So we're going to clear the registers. This is our ALU output and this is our data bus right here. This is our opcode and this is our operand. And you're going to see it go all in action. So we just put 2. So now we have 3, and then we have 5. Next we'll have 8, 13, 21, and so on. And we're going to continuously add until our carry gets high. And then once our carry gets high, we're going to restart the program essentially. And you can see we're going to jump back to up to program 6. And we're going to continue the loop of saving these numbers. Okay, so the carry should be high now, and we should restart the program very shortly. Okay, and then you can see we were back to 7, and 7 restarts the program counter. So now we're going back to the beginning. We're going to clear both the registers, and now we're going to restart our little program purely from the start. So we're going to load the numbers in and then continue our Fibonacci sequence. And that is essentially how the CPU works in its current form. A little thing I do want to point out too, this CPU isn't perfect. You can see I messed up with some of the designs in some places, but I managed to fix it. And so that means when I ever make this next computer, it's going to be fully perfect because I know exactly where the flaws are in the system, since I designed it all in kind of theoreticalness. And it turns out in practice, some of the things I thought would work wouldn't work, but most of it does work. And that's why we have only a very few problems right here. And so this computer is essentially pretty good in the first try, and I'm kind of proud of it. But now let's go to our instruction set architecture and our little code, and I'm going to walk through how this code exactly works step by step. So this is going to be our instruction set architecture video. I don't have all the instructions programmed into the microcode on the CPU, and I'm just going to show y'all real quick. So look back on here, this is our microcode, and then this is our actual code. And so the microcode pretty much just has the instructions on what the CPU should do or how it should execute the instructions. For example, if our code says we want to add and save to register A, we need to program something in here so we can make the computer add the numbers and then save it into register A. And we're going to use this ROM chip to decide what opcodes correspond to what physical execution process we should do. So we can pretty much design it however we want. We can make opcode 10 be saved to accumulator, or we can make opcode 1 saved to accumulator. And this is the little instruction set architecture that I came up with. It's purely arbitrary, you know. I could have picked any numbers I wanted. I just picked these. So all zeros is no operation. That should pretty much kind of be a given. And then we have 1 is load immediately to the accumulator. So what we're going to do is we're going to have our operand be a number, and we're going to load that number immediately into the accumulator. And then program 2 is going to be load immediately into register B. And then the way this computer is designed, if you remember from earlier, register A feeds into one part of the ALU, and then register B feeds into the other part of the ALU. So this too makes up our ALU. And then we have save A and save B. Since without any opcode, our ALU naturally just adds the numbers automatically. So this is essentially saying add and then save to the accumulator, add and then save to the register B, although it doesn't necessarily mean that, because we're just saving from the data bus. So whatever's on our data bus, we're saving that into a register. And since the only thing that can really be on our data bus right now is our ALU output, we're just saving that into the register. In the future, if we get like a little RAM chip and the RAM is sending data on the data bus, we need to kind of distinguish this and mess with the microcode a little bit more so we can decide if we want to save the ALU or save the RAM onto the data bus. But as of now, this is not a problem. And then we have jump is 7. So if 7 is our opcode, we're going to jump to a certain program of our choice, which is any number. So these just mean numbers. And then we have jump carry. So what this means essentially is if the carry pin is off, we want to jump to a certain place. But if the carry pin is on, we're going to skip over it and we're not going to jump. And so that's 8. So, and you'll see what this really means when we look at our code. And then we have clear, of course, which just clears all the registers. So now let's look at our actual execution of this with our program. So program 0 is going to be clear. We're just going to clear it all. And then the way the computer works too, if you remember from earlier, we have opcode, operand, opcode, operand, opcode, operand. And if it doesn't have an operand, then we're just putting nothing in the second part because it's irrelevant. And I could make it to where there's no blank spaces because that does cause some efficiencies within the program, but that would just be way too complicated and I didn't want to fool with that. So I just left it in there. So we have clear, we're going to clear the registers. Then we're going to load 1 into the accumulator. We're going to load 2 into register B. Then we're going to save the accumulator. So these two added together are going to give us 3. So we're essentially saving 3 into the accumulator. And then we're going to save in the B. And we're going to save 5 into B because accumulator A is going to have 3 and then B is going to have 2, which will give us 5. And then we're going to jump back to program 6, which is save A. And since our carry output is low because we haven't gone over 8 bits yet, we're just going to continuously jump back to 6 like this. But once our numbers go over 8 bits, we're going to skip this program right here and then jump back to 0 and reset the whole program. So that's a little brief description about how this code works. There's many other ways we could have coded the Fibonacci sequence into our computer, but this is the way that I just took just to make it a little bit easier on me and a little easier to troubleshoot, although it really wasn't that easy to troubleshoot. But hey, it works in the end, and that's all that matters. So now let's go into the next part of the video. So the next part of the video is actually the conclusion of this video. So thank you so much for watching. Again, look at NextPCB's links in my description. We also have the Discord link if you want to join this computer architecture Discord. Go follow me on Instagram. There's other links in the description too that you might be interested in. If you're interested in buying this design or you want a fully assembled 8-bit CPU, please comment below. I kind of want to take a poll with how many people are actually interested in buying a circuit like this for educational purposes or their own like curiosity. Because it's pretty small and it really gets the job done with teaching how computers really think and how code really works. But like I said, that is it for this video. Please come back next week and I'll be off for summer vacation, and hopefully I can start making more videos, more high quality videos, and we can keep diving in our education about how computers work and electrical engineering on this fundamental detail, and so much detail. Thank you so much for watching.